Today we're going to look at our biogeochemical cycles, which when you dissect that gigantic word, you see bio, that's life, geo, earth, and then of course the chemical components. We're talking about nitrogen, phosphorus, sulfur, carbon, and how they work their way through our environment through living things and non-living things. So we're going to start by grabbing these four cutouts. I'm going to give each of you one of these little strips to cut out, and that's going to be glued into our notebook, and we'll write around it. And while we're taking our notes, I'll show you some information, and then I'll pop up an example of what I wrote. You can definitely write more than that, but I'll show you what I wrote to kind of take this information and condense it down. So watch for that to pop up as we go. So we're going to start with I guess, not the simplest one, but the one that AP doesn't really concentrate on as much. There's a couple of questions about it, but they don't really spend a lot of time on the sulfur cycle. So you have a cutout of the sulfur cycle, so put that in the middle. And the sulfur cycle is the movement of sulfur through the atmosphere, through the ground, through the sediments there, and then through the plants and animals that consume that and work it through there. A couple of things to note about the sulfur cycle. The reason that they do talk about the sulfur cycle is sulfur is important to animals. That's how we construct our protein and vitamins. So in that regard, it's essential for animal and plant health. So we need the sulfur. But the problem comes when we have artificially pumped in too much sulfur to this sulfur cycle through burning coal. So normally everything is nice and balanced and the sulfur just moves through the system. But if we take too much of that sulfur out of the ground, out of those minerals, and release it into the air, that atmospheric sulfur, then we can overtake the levels, we can exceed the levels that are safe. And that sulfur will mix with the water vapor that's already in the air. And sulfur is a huge component of acid rain. So here's the notes that I took. It's important to have sulfur, but if you have too much, then it becomes a problem with acid rain. And we have actually increased the amount of sulfur in the atmosphere from burning coal. Okay, the next one that we're going to look at is the phosphorus cycle. So grab your phosphorus cycle, cut it out, put it in your notebook. And a couple of really notable things about the phosphorus cycle. Number one is the phosphorus cycle, if you notice here, doesn't have an atmospheric phase. They have the rain pictured here, but that's because that rain weathers rocks, and the weathered rocks release the phosphorus into the sediment, and then it enters the food chain. The plants take it up from the sediment, animals eat the plants, decomposers decompose both plants and animals. So it works its way from rocks to living things. And it is a necessary component of our bones and our teeth and our cell membranes, but there's no atmospheric phase of phosphorus. So the plants pull it from the soil and the water, the animals get it from the plants or from eating other animals that have it. And so that phosphorus cycle just continues on with animals and plants eating it and then decomposing back into the sediment, and one big cycle there. Okay. So here's what I wrote about the phosphorus cycle. The main thing that you'll see is there's no atmospheric phase. In fact, a question that you might see might be which biogeochemical cycle does not include the atmospheric phase? That would be the phosphorus. Okay, they love to ask that question. It is crucial for DNA and cell membranes. Plants get it from the soil, animals get it from plants. And then important reservoirs of phosphorus is our rock and our sediment. Okay? If we need more, we can add it. Just like some of our other chemicals, we can add it with fertilizer. All right, the carbon cycle, you might be a little bit more familiar with because of recent news articles about global warming. So let's break down the carbon cycle and see what the natural carbon cycle is like and then how we've changed it. So you should have a carbon cycle cut out. Put that down. Let's talk about carbon cycle, and then I'll show you what to put for your notes. So the carbon cycle is a way of cycling that carbon through many different types. Now, a carbon cycle does have an atmospheric phase, which is carbon dioxide, but you also have a liquid type of carbon. You have solids that include carbon. In fact, carbon is the essential building block of life. If you ever take organic chemistry in the future, it's carbon-based everything. So carbon is essential for life on Earth. It's the big thing that creates life here. That carbon is part of nucleic acids, carbohydrates, lipids, proteins, part of everything. You won't find a living organism without carbon. And as a result of that being so prolific in our environment, you get a lot of carbon in the atmosphere. You get a lot of it in sedimentary rock. In fact, the picture here is limestone, which is calcium carbonate, CaCO3. And then you get fossil fuels, which are old living things that have died, whether it's plants or animals, but over time they've been compressed and their carbon has combined and created what we call hydrocarbons, which is fossil fuels. So it could be coal, oil, natural gas that have been compressed for a very long time. That's called your old carbon. Those are those fossil fuels, the limestone. Those have been locked away in that reservoir for a long, long time. The new carbon is what's cycling between your living organisms. So the carbon dioxide that your plants take in for photosynthesis, the sugars that they create, that they hold on to, and then of course the carbon that moves through different life forms before we respirate it out as carbon dioxide again. That's our new carbon. So the problem exists when it gets out of balance. So here we've got our carbon cycle. One reason we are very interested in carbon dioxide is it is a greenhouse gas. The ocean is a big reservoir of carbon. You might see to sequester. The ocean will sequester carbon. That means it'll pull in carbon and hold on to it. Plants and animals use that carbon during cellular respiration. That's created by plants that lock it in during photosynthesis. The largest reservoir of carbon is sedimentary rock, that limestone, calcium carbonate. There's a lot of that around the Earth. Decayed organisms will lock in carbon into the soil, and then over time, if that's allowed to stay and become pressed and compacted, then that could become fossil fuels. And then once we burn those fossil fuels, or if we burn current sources of carbon, like trees and forest fires, then that carbon is released directly into the atmosphere. So it's very easy to kind of disrupt that balance of our carbon cycle. So our biological processes, one is photosynthesis. Photosynthesis takes that atmospheric carbon, that carbon dioxide, and fixes it into sugar, which is then used for energy by the plant and then by the things that eat the plant. Cellular respiration is kind of the opposite of photosynthesis. If you notice, it's exactly opposite. Cellular respiration takes those sugars that have been locked up by photosynthesis and uses it, breaks apart, takes that energy, and then we respirate out carbon dioxide and water vapor. You also get decomposition, which is when our decomposers convert any living matter that has died, so leaves that have fallen off of trees or animals that have past their lifespan. They'll take that and convert it into usable nutrients and carbon dioxide and return that to the atmosphere. And if you've ever smelt something decaying, it has that terrible odor. That's that CH4, that methane that gives you that terrible odor. That's caused by the decomposition process. We also have a couple of geochemical processes that will convert carbon back and forth. For instance, exchange has to do between the oceans and the atmosphere. The oceans will actually diffuse, they will take in carbon dioxide from the atmosphere and lock it away in the form of carbonic acid. Now, the oceans are gigantic. They can lock away a lot of carbon dioxide, but as they take in more and more carbon dioxide and they get more and more carbonic acid, then you get a process called ocean acidification. And that's kind of it goes hand in hand with that global warming trend that people are talking about a lot. Not only is the Earth getting warmer, they say, but also that increased amount of carbon dioxide, the ocean is a self-regulating mechanism. It's going to try to take that carbon dioxide out of the atmosphere and lock it away. But when it does, it gets more acidic, and that can be bad for the organisms that are living there. So it's just kind of this big feedback loop of things that are trying to regulate the planet and put it in balance, but end up causing problems as a result. Sedimentation is when living creatures like coral or your sea animals, like oysters and clams and anything that has a shell to it, your shellfish, they'll take carbon dioxide and calcium and make calcium carbonate. So coral is calcium carbonate. Limestone, the rock that we saw, is old dead coral, basically. Burial over a long time, when we bury organic carbon and that biomass is buried and there's been a lot of heat and pressure and time, then that burial can lead to the production of fossil fuels. Then extraction. We want those fossil fuels. They're very beneficial to us. So we remove the coal and oil and natural gas, and upon burning it, that combustion, then burning it releases that carbon back into the atmosphere. So whereas the process of exchange and sedimentation and burial are very slow processes, extraction and combustion are extremely fast. And that's what's getting that balance. We're taking it out and releasing it to the atmosphere faster than the atmosphere can regulate itself and remove that carbon and sink it back. So here's what I wrote for my carbon cycle. We had already written the part in the top. So start here with photosynthesis. If you've written already, by all means, keep what you've already written. Don't redo it. But I just kind of took each of those processes and just summarized them very briefly. Let me move myself so you can see the H2O. There you go. Next. Okay. So how are we impacting the carbon cycle? With the Industrial Revolution, we found a very efficient, very easy way of getting energy, which is to use fossil fuels. Could be coal, oil, natural gas. That has really changed our lives as humans and made our lives in some ways a lot better. We've gotten a lot more machinery, we've got a lot better transportation, our world is more connected, all because of fossil fuels. The problem, though, is that those fossil fuels burning has offset the balance between old carbon and new carbon. We are putting carbon into the atmosphere faster than our Earth processes can take it back out. So again, you've got problems with potential climate change because of that carbon dioxide being a greenhouse gas. And you've also got ocean acidification issues with the ocean trying to sequester that carbon dioxide and it causing that carbonic acid buildup. Then add to that deforestation. More people, more transportation, more technology. You need a lot more land to feed these people and house them. So when we take out the trees and the forest and the greenery that has already been there and has been trying to sequester and lock in that carbon, then you're putting it out, but you don't have anything to take it back in. So slash and burn techniques of forestry, not only do they take away the trees that would be taking in carbon dioxide, but they also take the carbon dioxide that's already in those trees and burn it and release it into the atmosphere. So you're adding more without having that sink to take it back out. So burning of fossil fuels and deforestation are your two huge problems that are causing this carbon cycle to be thrown off balance. Okay. So next video, we'll talk about our final biogeochemical cycle, which is the nitrogen cycle. So look for that video.